Chapter 6: Inflammation as a Structural Event. Inflammation begins when the membrane no longer maintains the conditions required for controlled exchange and stable signaling. It is not initiated as a standalone program. It emerges when the boundary that defines the cell shifts in permeability, packing, and organization. These changes alter ion gradients, protein positioning, and the availability of signaling substrates, producing a coordinated response that reflects the state of the structure. The system reacts because the physical conditions that support normal operation have been disrupted, and restoration of those conditions becomes the priority. Loss of packing density increases permeability and changes electrical balance. Ions that were previously contained move more freely, altering local charge and affecting voltage-sensitive channels. Calcium entry rises, triggering enzyme systems that respond to changes in intracellular concentration. These enzymes act on membrane lipids, releasing fatty acids that feed directly into signaling pathways. The sequence is continuous. Structural change alters ion movement, which activates enzymes, which then generate signals that further modify the local environment. Domain organization breaks down as the membrane destabilizes. Regions that previously concentrated receptors and signaling proteins lose their integrity, dispersing components across the membrane. This changes interaction patterns. Some pathways fail to initiate because clustering cannot be sustained, while others activate inappropriately due to new proximities between proteins that are normally separated. The result is a shift from controlled signaling to a mixture of activation and interference, where outputs are less specific and more variable. Fatty acid release provides a substrate for immediate local signaling. Phospholipids respond to changes in calcium and membrane state, liberating fatty acids that enter enzymatic pathways, producing eicosanoids and related molecules. These signals act within the surrounding area, altering vascular tone, permeability, and immune cell behavior. The profile of these signals depends on the fatty acids present in the membrane at the time of activation. The membrane therefore determines not only that a response occurs, but also the type of response that is generated. Reactive species reinforce the process by modifying membrane components. As electron leakage and enzymatic reactions increase, reactive molecules interact with lipids, changing their structure and further reducing packing stability. This increases permeability and accelerates domain disruption. The membrane becomes progressively less capable of maintaining gradients and organizing signaling components, amplifying the conditions that sustain the inflammatory response. Mechanical stress integrates with these changes. Deformation of the membrane alters tension and curvature, influencing how lipids pack and how embedded proteins respond. Mechanosensitive channels open under these conditions, further altering ion flux and reinforcing the signaling cascade. Physical and chemical changes converge, each reinforcing the other as the system moves away from its stable state. Signal propagation depends on the extent of structural disruption. Localized changes produce localized responses that can be resolved once membrane integrity is restored. Widespread disruption extends these signals across larger areas, increasing both intensity and duration. The scale of inflammation therefore reflects how broadly membrane structure has been altered and how effectively surrounding regions can maintain stability. Resolution requires rebuilding the membrane. Lipids must be replaced, domains must reform, and permeability must return to controlled levels. As structure is restored, ion gradients stabilize, enzyme activity normalizes, and signaling pathways return to baseline. The inflammatory response subsides because the conditions that sustained it no longer exist. This is not a separate process. It is the continuation of structural repair reaching a point where the system can resume controlled operation. Inflammation, viewed through this framework, is the system responding to structural failure at the membrane level. The pathways involved are known, but their activation is determined by the physical state of the membrane that houses them. When that state is stable, signaling remains controlled. When it is not, the same components generate a response aimed at restoring the boundary conditions required for normal function. Membrane damage as the trigger. The initiating event is a change in the physical state of the membrane that alters containment, not a discrete biochemical switch. When packing loosens or continuity is interrupted, permeability increases and the distribution of ions shifts immediately. Calcium moves along its gradient into the cell, raising local concentrations near the inner leaflet. This rise is not interpreted abstractly. It directly changes enzyme behavior. Calcium-sensitive phospholipids activate at the membrane surface and begin cleaving phospholipids, releasing fatty acids that feed into rapid conversion pathways. The signal begins as a consequence of altered flux across a compromised boundary. Damage also exposes lipids and protein domains that are normally sequestered within the bilayer. These exposed structures interact differently with surrounding proteins and extracellular components, creating new binding opportunities that were not present under intact conditions. Receptors that depend on defined orientation within a stable bilayer shift conformation when the surrounding lipids are disrupted. This alters their activity thresholds and increases the likelihood of spontaneous or low-threshold activation. The same receptor population produces a different output because the structural constraints that held it in a specific state have changed. Mechanical discontinuities propagate through the membrane plane. A localized defect alters tension in adjacent regions, changing how lipids pack and how proteins move. Mechanosensitive channels respond to these shifts by opening, further increasing ion flux and reinforcing the initial disturbance. This spreads the effect beyond the point of damage, creating a gradient of altered conditions that extends into neighboring domains. The signal therefore expands from a structural defect into a broader field of modified membrane behavior. Reactive modification follows quickly. Increased ion flux and disrupted electron flow generate reactive species that interact with nearby lipids. Oxidized lipids change shape and packing characteristics, introducing further instability into the bilayer. These changes increase permeability and disrupt domain organization, making it more difficult for the membrane to reestablish its original state. The system enters a reinforcing cycle where structural damage promotes chemical modification and chemical modification deepens structural disruption. Transport processes shift as a result. Channels and carriers embedded in the membrane rely on stable gradients and consistent lipid environments. When these conditions change, transport rates alter in ways that can either amplify or partially compensate for the disturbance. In many cases, the increased permeability overrides controlled transport, allowing passive movement to dominate. This reduces the system's ability to maintain separation between compartments, further eroding the conditions required for controlled signaling. The immediate consequence is the generation of local signals derived from a membrane itself. Released fatty acids are converted into short-lived mediators that act on nearby cells and structures. These mediators adjust vascular tone, permeability, and immune cell positioning, all within the region defined by the original structural change. The response is proportional to the extent of the damage because the amount of released substrate and the degree of altered flux scale with the size of the disruption. Containment determines whether the response remains localized or spreads. If surrounding membrane regions retain their integrity, they limit the propagation of altered conditions and confine signaling to the site of damage. If adjacent regions are already unstable, the disturbance extends outward, producing a larger field of activation. The membrane either isolates the event or allows it to expand depending on its baseline condition. Membrane damage functions as the trigger because it directly alters the parameters that govern ion movement, enzyme activation, and protein behavior. The subsequent signaling pathways are engaged because the structural environment has shifted, not because a separate decision has been made. Restoration of the membrane reverses these conditions. Ion gradients reestablish, enzyme activity returns to baseline, and the signals generated from the disruption diminish as the boundary regains its capacity to contain and organize the system. Omega-6 and omega-3 balance as substrate competition. The balance between omega-6 and omega-3 fatty acids is determined at the level of the membrane as a question of occupancy and access. Both classes are incorporated into phospholipids and held within the bilayer as potential substrates. When activation occurs and phospholipids release fatty acids, these substrates compete for the same enzymatic pathways. The outcome is not decided after release. It is largely predetermined by which fatty acids are present in the membrane and in what proportion. The system draws from what is already embedded in its structure, so composition sets the direction of signaling before any stimulus is applied. Once released, these fatty acids enter shared conversion routes. Cyclooxygenase and lipoxygenase enzymes do not selectively process one class in isolation. They act on available substrates, and the relative abundance of each determines which products are generated in greater quantity. Omega-6 derived substrates tend to produce signaling molecules that promote vascular constriction, increase permeability, and immune cell recruitment. Omega-3 derived substrates enter pathways that yield signals associated with controlled resolution, reduction of excessive permeability, and restoration of baseline conditions. These outputs are not opposites in an abstract sense. They represent different structural responses to changes in the membrane environment. Competition occurs at multiple stages. It begins with incorporation into the membrane, where both omega-6 and omega-3 fatty acids occupy positions within phospholipids. It continues during release, where enzymes act on available lipids without preference beyond accessibility. It persists through conversion, where enzymes process whichever substrate is most available at that moment. At each stage, the relative presence of these fatty acids determines which pathways dominate. A membrane enriched in one class will produce a corresponding profile of signaling molecules because those substrates are more likely to be released and converted. The physical properties of these fatty acids also influence how they behave within the membrane. Differences in chain structure affect packing, fluidity, and the formation of domains. These structural effects alter enzyme access and protein localization, indirectly shaping which substrates are processed. A membrane with altered packing characteristics may expose certain fatty acids more readily or position enzymes in a way that favors one pathway over another. The competition is therefore both chemical and structural, governed by how these molecules are arranged within the bilayer. Signal duration and termination are affected by the same balance. Products derived from different substrates have different lifespans and rates of degradation. If one class dominates, its signaling molecules persist and shape the local environment for longer periods. This influences how quickly the system can return to baseline after activation. Efficient resolution depends on the availability of substrates that support pathways leading to termination and repair. If those substrates are limited, signals associated with activation continue to dominate, extending the response. The balance between omega-6 and omega-3 fatty acids does not act as a simple ratio in isolation. It reflects the composition of the membrane and the distribution of substrates within it. Changes in this balance alter the set of signals that can be generated, the rate at which they are produced, and how long they persist. The system does not choose between pathways independently of structure. It follows the constraints imposed by the substrates available within the membrane at the time of activation. Substrate competition, therefore, defines the direction of local signaling by determining which pathways receive input under conditions of activation. The membrane acts as the source of these inputs, and its composition dictates the outcome before enzymatic processing begins. Adjusting this composition changes the signaling landscape by altering which substrates are available to compete, thereby shifting the profile of responses generated when the system is engaged. Resolution pathways and failure to complete. Resolution is not a passive fade-out of signaling. It is an organized sequence that depends on a shift in membrane-derived substrates, reassembly of domains, and restoration of controlled flux across the boundary. Once the initiating disturbance has been contained, the system must transition from generating activation signals to producing mediators that terminate the response and rebuild structure. This transition is constrained by what remains in the membrane. If the lipid environment supports the generation of resolving mediators, the system proceeds toward completion. If it does not, the initial response continues to cycle because the conditions required to terminate it are absent. The switch begins at the level of substrate use. As activation progresses, the pool of released fatty acids is redirected into pathways that generate resolving molecules rather than additional proactivation signals. This redirection requires both the presence of appropriate substrates and the positioning of enzymes that convert them. When these elements are aligned, local signaling shifts from increasing permeability and recruitment to tightening the boundary and clearing accumulated intermediates. Vascular tone normalizes, immune activity contracts to the site of need, and excess signaling molecules are degraded or reincorporated into the membrane. Spatial organization determines whether this transition occurs cleanly. Enzymes responsible for resolution must operate in the same regions where activation took place. If domain structure is intact, these enzymes access substrates efficiently and terminate signals at their point of origin. When domains are unstable, substrates and enzymes are no longer co-localized. Activation pathways continue because their components remain active, while resolution pathways lag due to loss of access. This creates a mismatch where initiation outpaces termination, extending the duration of the response. Termination also requires restoration of ion gradients and electrical stability. As membrane permeability decreases and packing improves, ion flux returns to controlled pathways. Calcium levels fall, reducing activation of phospholipids and other enzymes that drive signal generation. This shift reduces the release of new substrates and allows existing signals to decay. If permeability remains elevated, ion flux continues to stimulate activation pathways, preventing the system from exiting the response state. The membrane remains in a condition that supports continued signaling rather than completion. Failure to complete arises when structural repair does not keep pace with signaling demand. Damaged lipids persist, domain organization remains fragmented, and gradients cannot be fully reestablished. Under these conditions, resolving pathways are present but insufficient. Signals that should terminate are replaced by new signals generated from ongoing structural instability. The system appears to be active continuously because the trigger condition has not been removed. Each attempt at resolution is interrupted by new inputs generated from the same compromised membrane. Reactive byproducts reinforce this failure. Oxidative modification of lipids alters their behavior and reduces the ability of the membrane to return to a tightly packed state. These modified lipids can continue to serve as substrates for signaling, extending the response. At the same time, they impair the formation of domains required for coordinated termination. The system becomes trapped in a cycle where structural damage sustains signaling, and signaling contributes to further structural disruption. Clearance mechanisms depend on the same structural conditions. Cells and enzymes responsible for removing debris and resolving intermediates must operate within a stable environment to function efficiently. When the membrane remains unstable, these processes slow or become misdirected. Accumulated intermediates persist, interacting with surrounding components and maintaining activation. The boundary is not restored, so the system does not return to baseline. Completion requires that the membrane reestablish its role as a controlled barrier. Lipid composition must shift toward configurations that support tight packing, domain formation, and stable gradients. As this occurs, substrate release declines, resolving mediators dominate, and signaling pathways shut down in sequence. The response ends because the structural conditions that sustained it have been removed. Resolution pathways succeed when structure is restored faster than new disruption occurs. They fail when the membrane remains in a state that continuously generates signals. The difference is not in the presence of resolving mechanisms, but in whether the underlying architecture allows those mechanisms to operate to completion. Chronic inflammation as incomplete signaling. Chronic inflammation reflects a system that initiates a response but cannot carry it through to termination because the structural conditions required for completion are never restored. The membrane remains in a state that continues to generate activation signals while simultaneously impairing the pathways that would normally shut those signals down. The result is not a constant high-level response, but a persistent cycle of partial activation, failed resolution, and reactivation driven by the same underlying instability. The process begins with a disturbance that alters membrane packing, permeability, and domain organization. Ion gradients shift, calcium levels rise, and enzymes release fatty acids that enter signaling pathways. Under normal conditions, this sequence would transition into resolution as membrane integrity is repaired. In the chronic state, repair does not reach a level that restores containment. Permeability remains elevated, allowing continued ion flux that sustains enzyme activation. Each attempt to terminate the signal is interrupted by new inputs generated from the same compromised structure. Substrate availability reinforces this cycle. The membrane continues to supply fatty acids that feed into activation pathways, while the substrates required for resolution are either insufficient or not effectively converted due to disrupted enzyme localization. The balance remains tilted toward ongoing signal generation. Even when resolving mediators are produced, they are outpaced by new signals because the source of activation has not been removed. The system attempts to complete the response, but the conditions necessary for completion are not present. Domain instability contributes to the persistence of signaling. Without stable regions to localize receptors, enzymes, and termination machinery, interactions occur without coordination. Activation pathways may initiate in one region while termination processes are delayed or displaced. Signals overlap and extend beyond their intended duration because the spatial organization required for clean sequencing is absent. The system operates with reduced precision, where timing becomes inconsistent and signals fail to resolve into discrete events. Electrical instability adds another layer. Fluctuations in membrane potential alter the behavior of channels and receptors, shifting activation thresholds and prolonging signaling states. Ion transport systems respond to these fluctuations, but their adjustments cannot stabilize the environment if the underlying membrane remains permeable. The system compensates continuously, but compensation does not equal restoration. Energy is expended to maintain function, yet the baseline condition remains altered. Reactive modification maintains the structural defect. Lipids exposed to ongoing stress are oxidized or otherwise altered, preventing the reformation of tightly packed domains. These modified lipids continue to influence membrane behavior, sustaining permeability and disrupting protein localization. The membrane becomes a persistent source of activation because its composition no longer supports the conditions required for termination. Chronic inflammation, therefore, represents incomplete signaling. The initiation phase proceeds, but the resolution phase cannot fully engage because the structural framework that supports it is compromised. Signals are generated, partially processed, and then renewed before they can be cleared. The system remains active not because it is intentionally sustaining the response, but because it cannot reach the structural state that would allow the response to end. Restoring completion requires restoring the membrane as a controlled boundary. Packing density must increase, domains must reform, and ion gradients must stabilize. As these conditions return, activation pathways lose their continuous input and termination mechanisms regain access to their targets. The signaling cycle can then proceed from initiation to completion without interruption, allowing the system to return to baseline rather than remaining in a state of persistent partial activation.